guys, today we're going to be learning how to do the selection sorting algorithm, insertion sorting algorithm, and merge sort algorithm. So let's get started. So we have this array and we're trying to look for the smallest index in the unsorted part of the array. This is going to represent the unsorted part of the array, and this is going to represent the sorted part of the array. So first, the selection sorting algorithm is going to look for the smallest, well, in this case, the smallest volume of water in a bottle, and it's going to search through the entire array. So which one is the smallest? It's going to look through the entire array, and then it's going to recognize that this is the smallest of value inside the array. So we're going to have this, and then it's just going to move, everything's going to move. Because since it only switches at one time every comparison. Okay, so then the computer is going to say, this is the sorted part of the array, and this is the unsorted part of the array. So then it's going to try looking for the minimum value in this part of the array, the unsorted part of the array. So it's going to look, which one is the smallest, which one is the smallest. Then it's going to recognize that this is the smallest value in the array. So then it's going to do that. It's going to move everything like that. So then the computer is going to recognize that this is sorted and this is unsorted. So it's going to look for the smallest value inside the unsorted part of the array, and it's going to look, and it's going to recognize that this is the smallest value in the unsorted part of the array. So then this and that are going to switch. This is going to switch until it becomes the first value after the unsorted, after the sorted part of the array. It's going to come here. Put that there. Okay, so then the computer is going to recognize that this is sorted and this is unsorted. So then it's going to do the same process again. Small, my bad. This, and this is going to switch with that. It's going to switch with the minimum value, and it's going to move that there. And then you're going to have this. Ignore this. You're going to have this is the sorted part of the array. This is unsorted. Then we're going to do the same process again. We're going to look through this part of the unsorted part of the array, and we're going to recognize that this is the smallest. That is going to switch. And we have that. And then it's going to recognize that this is all sorted. We'll do that so this is all sorted and this is unsorted. And then finally it's going to say which one is smaller? This one. It's going to put that there, here. Then after it does that, the entire array is sorted. This entire array has been sorted through selection sort. Before you move on to insertion sort, I just want to point out that selection sort, the time complexity is O of n squared, and since there were 7 water bottles, that represents the length of the array. It's going to be 7 squared. O of 7 squared, which is 49. O of 49. So let's move on to insertion sort. So insertion sort works like this. We're going to have these two first values in the array, and we're going to compare them. Which one is greater and which one is smaller? This one is smaller than that, so this is going to switch with that. I'm going to move the entire array down. So we're going to do the same thing here. Is this one greater than that and less than that? Since this is already greater than that, we're going to leave this. So this is going to be sorted, and this is going to be unsorted. Insertion sort is weird in the fact that you will still switch the sorted part of the array. It'll get more clear after we sort this. So then we're going to have this part, and we're going to compare this part to this, to the first value here. Is this one greater than that? No, so it's going to switch. Boom, boom. And then it's going to say, is this one greater than that? No. So then the entire array is going to shift down. So then we identify that this is sorted. So then it's going to do the same thing here. Is this one greater than that? No, so we have to switch. And then it's going to say, oh, is this one greater than that? Yes, so it's going to go in between those. So then we have this. Boom and boom. So then we're going to do the same thing here. Is this one greater than that? Yes, so this is going to switch. And then it's going to say, is this one greater than that? No, so it doesn't switch. So we have all, or I used the wrong color. We have all of that, and this is unsorted. So then we're gonna do the final switcheroo. It's gonna compare themselves. Can it fit in between that and that? No. Can it fit in between that and that? No. This and this? No. This and this? Let's compare. This one is greater than that. This one is greater than that. And this one is less than that. So then it's just going to go right inside those two values. Right in between them. And then you have it completely sorted. Before moving on, I wanted to point out the complexity of insertion sort. So selection sort, the array always looks for the minimum and then switches like that. Except for selection sort, it's the time complexity is always going to be O of n squared. Insertion sort has many time complexities. In the worst case, meaning the longest amount of time it will take for the computer to do everything, will be O of n squared, similar to selection sort. But the worst case is going to be when the values in the array are in the reversed order, so it'd be 4, 3, 2, and 1. And the best case would be O of n. So the best case would be when the values are already sorted, 1, 2, 3, 4. Then again, for selection sort, even if it's already sorted, it's going to take O of n squared. However, for insertion sort, it's only going to take O of n or O of n squared for the computer to compute. And in this case, O of n squared is going to be 49. And O of n is just going to be O of 7. So let's move on to merge sort. Here we are, finally, merge sort. Merge sort is going to be your worst enemy when tracing, but after some practice, you'll sort of get it. So merge sort works like this. We have our array, right? We're going to get the length of the array. So 1, 2, 3, 4, 5, 6, 7, and we're going to divide it by 2. Similar to binary search. 7 divided by 2 is going to be 3.5, but since this is coding, it's going to be 3. So the first half of the array is going to be boom, boom, boom. The second part is going to be that. So we have 2 parts of the array. We just separated the array into 2. Of this. 2 separate arrays. And then we're going to do something even worse. The computer splits the array again. So we're going to have this and this to be together. This and this. Done that. And this and this. And this is going to be a lone boy. So we have these separated arrays. And then it's important to know that whenever an array is by itself, it's already sorted. And the computer kind of uses that in its logic. So it just separates the array again. So this are separated. This and this have been separated. I'll put them close together. So that and that are separated. This and this have been separated. This and this have been separated, and that has been separated. So then we have 7 separated arrays. Then the computer decides to put them all back together. So wait, let me. Actually, it's since this is sorted, and sorted. The computer decides to put all of these sorted one bottle arrays together. except when it puts it together, it's going to sort it while it's putting it together. So this and this have to, since they were separated, they're going to merge again, except it's going to be sorted. So it's going to say this is going to go in, this is going to go, since it's greater, it's going to go here. So then, look, it's wrong color again. This is going to be sorted. So then we're going to do the same thing here. We're going to put that there. This is smaller, so it's going to put that there. Now this is sorted. Same thing here. Smaller, bigger, put them back together. Sorted. And this lone boy, he's already sorted. Okay, so now we have 4 sorted arrays. The computer decides to put them back again. So these two are originally together. The computer is going to merge those. And these two are originally together. The computer decides to merge those. So then it's going to do this. Then the computer is going to compare this one and this one. And it's going to say which one is smaller, this one or this one. It's going to say this is smaller. So then it's going to get this one, and it's going to compare that and that. Which one is smaller? This one. Then it's going to compare that and that. Which one is smaller? Boom, boom. This one is smaller. So then this array has been sorted, and then we're going to do the same process here. It's going to compare this one and this one. Which one is smaller? This one. Then since this is already a sorted part of the array, it's just going to combine it again. So then this has also been sorted, and this has all been separated from one huge array. Okay, and then we're going to combine these again. Same process. This is sorted, and that has been sorted. And then it's going to compare this index from this index. Which one is smaller? Boom, or this one? This one is smaller. So then this is going to be there. And it's going to compare this one. This one is smaller, this one, this one. Then it's going to do the same thing. Boom. Boom. Which one is smaller? This one, this one, this one. And then since this is already a sorted part of the array, it's just going to put everything back together. And what do you know? The array has been sorted. And that has been merge sort. It's definitely one of the harder ones to memorize, but it's really fun when you actually trace it. Really here, merge sort. So the time complexity of merge sort. So I forgot to point out something with insertion sort. Insertion sort, usually most of the time, it's going to be n squared, O of n squared. And the only real advantage to insertion sort over a selection sort is that selection sort's always going to be O of n squared. However, insertion sort, even when the array is sorted, except when insertion sort, when the array is sorted, it's going to be O of n. O of n, there it is. So another merge sort. Merge sort, it's so complicated to do in your head. Well, it's not completely complicated if you practice. Except for with merge sort, the time complexity is O of n times log base 2 n. And that's going to be in all cases. So even when it's reversed, even on its average, even when the array is already sorted, it's going to take n times log squared n. So on the average, best, and worst case scenarios for the array. So then we're going to calculate this. 7 log base 2, 7. And in general, for coding, whenever it just says log, the base is always going to be 2. It's never going to be 10 like normal math. It's just going to be 2. So then we're going to have 7 times log 2, 7. And to my dismay, I do not have a calculator. I'll be right back. Let me calculate this. So I'm back, and I've calculated it. So O of log 2, 7 to the power of 7. You know your log properties. This will go inside there. And then you'll have O of log base 2, 7 to the power of 7 would be 8, 2, 3, 5, 4, 3. So you have O of log base 2, 8, 2, 3, 5, 4, 3. And when you calculate that, that's going to equate to 19.6515. O of 19.615. And as you can see, That is way better than O of 49, but not as good as, like, for example, O of 7, except consistently merge sort will always be the winner if the array is not already sorted, and in that case, an insertion sort would win. Therefore, merge sort is the best out of these two. Thank you for watching.